Lewis dot structures for compound. So let's draw Lewis dot structures for some compounds. The first thing we're going to look at is ionic bonds. Remember, ionic bonds are between a metal and a non-metal. So let's take a look at the first example, KBr. So we know that K is a metal and Br is a non-metal. And we'll go to the periodic table and we can see that K has a valence electron of 1, while Br has a valence electron of 7. So that means that K is going to want to give away its electrons to Br. Okay, so let's go ahead and write down the valence electron. So there's 1 valence electron here and 7 valence electron there. So to write the Lewis dot structure, remember we first write down the symbol. So we're going to write down K, and we're going to write down Br over here. Okay, and remember that because K is given away its valence electron, it would actually have no valence electron around it, and that we will now have a charge of a positive 1. So we're going to write K with a bracket and just put a positive sign to indicate a positive 1. Now Br actually is gaining an electron, so therefore now it's going to have 8 valence electron around it. So we're going to put 8 valence electron around it. And we're going to put the bracket. And we're going to put a negative charge to indicate that it gained a valence electron. Let's take a look at a second example, CaCl2 or calcium chloride. So in this example, we see that calcium is a metal with a 2 valence electron, while chlorine over here is a nonmetal with a 7 valence electron. So we know that's a metal and a nonmetal, so it's going to form an ionic bond. So let's write this out. So calcium has 2, okay? So we're going to put 1, 2, and 2 over there. And then chlorine has 7. So we're going to put 1, 2, 3, 4, 5, 6, 7. But there are 2 chlorine, as we see from this compound. So we need to do another chlorine over here. 1, 2, 3, 4, 5, 6, 7. Okay. So this means that one of the calcium electron can be moved over here to make this a octet, and the other calcium can be moved over here to make this an octet. So therefore, when we rewrite this, we saw that calcium lost 2 electrons, while chlorine gained electron each. So let's actually write out the Lewis dot structure for this. So we have calcium. It will have a 2 positive charge to indicate 2 electron loss. And then we will write chlorine on both sides with the full octet. We draw the bracket, and that's a negative charge. Same thing over here. Is have a full octet with the bracket, and a negative charge is so that it gains an electron each. And this right here is the Lewis dot structure for calcium chloride. In our next example, we have lithium fluoride, which is lithium is a metal with 1 valence electron, and fluorine is a non-metal with 7 valence electrons. So lithium is going to give away its electron, and fluorine is going to accept it. So let's go ahead and let's draw the Lewis dot structure for this. So the Lewis dot structure is L, I. We draw a bracket around that. We show it's a positive sign to show that's been given away. And then we're going to draw fluorine next to it. And fluorine now has 8 valence electron, so we're going to put 8 valence electron around it. So we're going to put 1, 2, 3, 4, 5, 6, 7, 8, and then we're going to draw a bracket around it, and we're going to put the charge, and in this case it is a negative charge. So our next example is magnesium iodide. It is very similar to the calcium chloride example we have here. Magnesium has 2 valence electrons like calcium, and iodine has 7 valence electrons like chlorine. So let's go ahead and draw that. We're going to write Mg. We're going to put it a 2 positive for giving away 2 valence electrons. It's going to give 1 to the first iodine, which now has 8 valence electron with a negative charge, and then another iodine over here with also 8 valence electron, and it also has a negative charge. So that is how we write the Lewis dot structure for magnesium iodide. So let's take a look at Lewis dot structure for covalent bonds. And remember, covalent bonds are bonds between 2 or more nonmetals. So let's take a look at NH3. So N is a nonmetal, and so is hydrogen, which is a nonmetal. And in this case, we have 4 total atoms. So in the rules, we would need to first consider is which one goes in the middle. So normally we will put the atom with the least electronegativity in the middle. So in this example, nitrogen is 3.0 while hydrogen is 2.2. So you assume that hydrogen would go in the middle. However, there's one exception to this rule, and that hydrogen is always on the outside and never in the middle. So we're going to write nitrogen in the middle, and then we're going to put hydrogen around it. So we're going to write just like this. Now, the next thing we're going to do is we're going to count the number of valence electrons that is in this compound. So based on the periodic table, we know that nitrogen has 5 valence electrons and hydrogen has 1 valence electron. So let's add it up. So that means that nitrogen has 5 plus 1, but we have 3 of that. So ultimately we have 8 valence electrons. So we have to put this 8 valence electron around this compound. Remember that in a covalent bond we are sharing. So the next step we're going to do is that we're going to put 2 electrons in between each of these atoms. So we're going to put 2 right here, and 2 right here, and 2 right here. So let's go ahead and count. That's 2, 4, 6. So that's a total of 6 valence electrons, and we know we have a total of 8. Okay, so hydrogen already have its maximum, which is 2, but nitrogen can actually get 2 more. Okay, so if we put 2 more right here, we now have 8 valence electrons, total 2, 4, 6, 8, and nitrogen has its maximum of 8 valence electrons. Now, normally we don't leave the dots as is. We actually, each of these dots pair can be rewritten as a straight line. So therefore, instead of 2 dots between the H and the N, we can actually draw a straight line to indicate a pair of electrons. So there's a pair of electrons between H and N here, another pair here, and another pair here. And this is how we normally see the Lewis dot structure for the NH3 compound. So let's now take a look at our next example. In our next example is N2H4. So let's go ahead and write down our symbol. So we have N, and then we have 4 H's. So we're going to put 1 H on each side, and then we're going to put an H on top of each of the ends. Okay? So the next thing we're going to do is we're going to go in and we are going to calculate the number of valence electrons. So again, N has 5 valence electrons, and there's 2 of that, so that should be 10 valence electrons. And H has 1 valence electron, but there's 4 of that, so that will give us a total of 14 valence electrons. Now we're going to go in and we're going to put in a pair of electrons between each of the elements. So we're going to put between each of these. Let's count our valence electron. That's 2, 4, 6, 8, 10. We have 10 here, but we should actually have 14. So that means that we need to put 4 more valence electrons between these elements. So let's count already. We have the maximum allotted one for hydrogen. So hydrogen cannot take any more. So we know we cannot add any more valence electron around hydrogen. So let's see whether or not we have the required 8 valence electron around nitrogen. We have 2, 4, 6 here and 2, 4, 6 here. So how can we make it so that we can have a maximum of 8 valence electron around each of the nitrogen? In this case, all we have to do is put 2 more here and 2 more here, and now we have a total of 8 valence electron around each of the nitrogen, and that will be our Lewis dot structure. So now let's take a look at a third example, N2H2. So let's go ahead and write those symbols out. Let's count the number of valence electron. That is 10 plus 2 is 12. Let's put the pair in between. Let's count them. That's 2, 4, 6. There's 6 and we should have 12. Since we already have the max around the 2H, we know that the rest of the valence electron must be around the end. Let's count the number of valence electrons around the first end. There's 4 around the first end and there's 4 around the second end. So we have 6 more valence electrons that we need to distribute among this. So let's go ahead and put our additional 2 around here on top of the end, and that gives us 2, 4, 6, and then 2, 4, 6. So that gives us 2, 4, 6, 8, 10. 10 valence electron, and we have 6 around each. So that means each nitrogen needs 2 more valence electrons. So a total of 4 valence electrons. However, we only have 2 valence electrons left, so we cannot distribute and put the valence electron down here, because then that will mean we have too many valence electrons. So what does that require us to do instead? What we can do instead is put the 2 valence electron in the middle. And we put in the middle, we now have 2, 4, 6, 8 around N, and 2, 4, 6, 8 around N. And so now we have a total of 2, 4, 6, 8, 10, 12, and that is 12 valence electrons. So we can't write it like this, and we're going to rewrite it with the lines. Now our last example is for F2. So first we're going to write down the symbol. So we will have 2 of them. And then we're going to count the number of valence electrons. Remember there's 7 of each, so that is 14 valence electrons. So let's go ahead and put 2 in the middle. So we know we have 2 there. So we're going to go ahead and we're going to put the valence electron up here. So we put here the 2, 4, 6, 8, 10. I still have 4 more. So I have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 10, 12, 14. That is a total of 14 valence electrons. Again, the pair that is shared, we don't leave it as dot, and we're going to rewrite them. And that is how we write Lewis dot structure for covalent bond.